Thank you, Noel. I have to press a button to make it go live. All right. Hello, everyone who's online, and hello, everyone who's here in person in class. So I would like to welcome you all, first of all, to this class, Chemistry in Our World. It's a very large class, and you may not know that by looking around, but I can see there's 210 people also on the YouTube stream right now. So that means there's 350 of us as of lunchtime today, and that number tends to go up just a little bit in the first week or so. So hopefully we can make sure everyone has a great experience. One thing, okay, so what I'm going to be doing is going through today kind of the basic expectations that I have from you for this course, what you can expect, and hopefully we can all have a good time. It's a little bit weird for me teaching because I don't see it really, I see your eyes, but that's really all I get to see. So it's a little bit, you know, I can't read your expression that much. So help me out. If there's something that's not going well, if I'm not speaking loud enough, if something's not clear, please feel very free to stop me and just let me know. So my name is Matt Lukeman, and I'm going to be your professor for the semester. On this first slide, basically what I have for you is just my email address, phone number. That's my office phone number, which that's probably not the best way to reach me, but it's there. My office is in Elliott Hall, which is the one at the bottom of the street closest. Am I pointing even in the right direction? That way. Across Main Street from the gym. So if you're looking for where I am, that's where my office is, in the basement. Obviously, you know the time of the course because you're all here. And for office hours for this course, because there's so many people and because the requests for office hours are a little bit irregular, I'm just going to say they're by appointment. So if you want to chat with me about anything, I'm very happy to do so. And rather than like fix a certain period of hours that you have to see me in those hours, it can really be any time. As long as I'm free and you're free, we can set up a time and then we can meet that way. Makes things a little more flexible and hopefully gives you some more options compared to what is ordinarily there. So I want to tell you just a little bit about myself before we get too deep into the course today. I grew up in Antigonish. I'm just getting some messages here too that are not just, I'm not just getting random texts. These are relevant. Great. Perfect. So grew up in Antigonish. If you're from Nova Scotia, you probably know where Antigonish is. Probably have been there. If you're not from Nova Scotia or maybe new to the province or new to Canada, it's basically about a 2.5-hour drive away. And this is a picture of me and my 3 brothers. Can you guess which one I am? I don't look like this anymore. I'm number 2. So second tallest, there we go. I went to St. FX, and I know, yeah. But I studied chemistry at St. FX, which is why I'm teaching chemistry now. And this was my graduating class. This was 1999. So probably a lot of you are thinking, I was born in 1999. Which, yeah. There we go. When I finished my degree at St. FX, I didn't know what I wanted to do with my life. I didn't know what career I wanted to have. And so what I decided to do was go to graduate school. Because in the sciences, if you go to graduate school, you get paid to do it. And it seemed to me like a bit like a snooze button. I could hit the snooze button and then decide later what I wanted to do with my life. So I went all the way to UVic, the opposite end of the country, still near the water, and studied to do my PhD there. This is a picture of UVic, and it is very close to the water there. Beautiful campus. It's a ring. This is called Ring Road. All the campus is inside. And when I was there, at least, there was rabbits everywhere. This would be like a typical view if you're outside on the campus. And these were like pets that people had just let go. And they're not wild rabbits. But I think they exterminated them all since then, since I left. I left in 2003. I don't know how they did this. They were a problem, though, because they would dig underground all the time, and they would start chewing on underground wires, which were a pain. And they'd also attract predators to campus, like cougars and things like that, which they also didn't really like. So I could see why they got rid of them. After I finished my degree in 2003, I finished in December, started in January 2004 at the University of Ottawa as a postdoctoral fellow. So that means basically as like a research job that you do fresh out of a PhD to gain some maybe more experience in a different area. University of Ottawa was quite different. It's very urban, very dense, very packed, not very much green space. Not as much green space as this artist's rendition makes it look like there is, but anyway, it was nice all the same. That's a picture of a very small part of my group. I'm in the very back. You can barely see me. But anyway, yeah, we had about 25 people in that particular research group. I wasn't there very long, about a year and a half, when the opening came up here at Acadia. And I applied. Actually, we had a snowstorm during the day that I interviewed, so campus was closed. So basically what they did is they added a day and they crammed 2 days worth of interviews into one. And that worked out, I guess, because I got hired. And I started here in 2005, in June. And here's a picture of my very first year here. This is the first summer that I had a research group. This would be the summer of 2006. And I'm a lot younger looking then. I was, I think, 26 when I first started working here. I'm not 26 anymore. You can do the math. So there's a picture of me now. It's my family. And yeah, happy to be here. I've been teaching this course for probably 10 years. I think it's pretty well developed. I think people enjoy it. Hopefully you enjoy it. And today we're going to introduce you to the course, talk a little bit more about, what's going to be happening. First of all, Acorn. Acorn is going to be used extensively in this course, okay? Presumably everyone here is familiar with Acorn, that you've used Acorn in lots of other classes. All of the lecture notes, all my PowerPoint slides is what I mean, are going to be going up on Acorn. I also post other sort of study guides, things like this at random times throughout the course. We will have maybe links to reading material posted now and then. All communication from me to the class will be done through the general announcements feature through Acorn. That means if you miss an email from me, you can go back and click on the announcements thing at the top of Acorn and read all of my past emails. So emails will never be lost for this course. Online lectures as well. I'm planning to do them all via YouTube Live. And so basically, if you want to reliably get onto the YouTube live stream, really what you need to do is go on Acorn and check the link that I put up. Or if you subscribe to the YouTube channel and just go there when the time for the class happens, you can just jump into the stream and hopefully everything there will work out fine too. Okay. Grading scheme. Another important piece that everyone would really like to know about, and I'll be talking about these different components separately as well. Unit assignments, 50%. It's half your grade. It's a big chunk of your mark for something called unit assignments that I'll describe in just a minute. There will be one written assignment and one video assignment worth 15% each, and a final exam worth 25%. And if you add all these numbers up, you might notice that they come to 105. They don't come to 100%, they come to 105. So what I'm going to do is, at the end of the semester, whichever of these 4 grades is lowest, whichever you did worst in of these 4 categories, I'm going to just take 5% off that. So let's say you really blew the final exam. That makes your final exam worth 20 rather than 25. And that's just a little bit of flexibility, because what that does is, it's a very wide, diverse class, lots of different people from different backgrounds coming in, and you might be strong in one area, somebody else might be strong in another, and that just kind of levels the playing field a little bit. Okay, all of the grades I will be giving you for this course will be percentages, or maybe like 8 out of 10, which you can make a percentage quite easily. And this is just a guide, because at the end of the semester, you're going to be getting a letter grade. And this is just the conversion factor to take your percentage scores up to this point, convert it to a letter grade. This was recently adopted by the Senate here at Acadia. I think all courses are supposed to be using this now. One change which is good for a lot of people, is the range for A+ has widened. It's now 90 to 100, and it used to be 94 to 100. Like this time last year, it was 94 to 100. Makes it a little bit easier to get an A+. But I think if you're below A-, nothing really has changed. I think these are all basically the same as they have been for those grades for a long time. So this is what I'll use to convert the grades I'll be giving you to the grades that I give to the registrar's office at the end. So the unit assignments, this is the big chunk. This is the biggest part of your grade for this course. And this will come in the form of one assignment for every unit that we cover. And a unit could be anywhere from like one class, maybe up to like 5 classes. So they'll range in size. And if you go on Acorn right now, what you will see is there is a question there. You can see the first quiz for the first unit already up, and I think the first one has 5 questions. And what I'm going to be doing is since we're going to have these for every semester, we'll be adding these up as we go. And the value for each unit assignment will depend on the number of questions. So if this assignment has 5 questions, it'll be worth half as much as, say, another assignment that has 10 questions. And so basically what I'm doing is I'm just counting up all of the questions and all of the assignments as we go. So what I'm planning to do is for most of these questions is actually deal with them during lecture in class, have them up on the screen. So if you have your quiz open on your computer with you as you're doing the lectures, you can actually sort of follow along and complete them as we go. So really, these could be like no work at all if you're attending class and you're paying attention and going along. And to me, that's a pretty easy way to pick up a substantial part of your mark for this course. Once the unit is complete, the assignment will stay live for 1 more week after that. So if you miss a class and the lecture is going to be posted online, if you then go and check out that lecture 2 days later, you can still do the same thing, go through the class online, go through the assignment questions up to a week after. After a week it closes and then that's it. So there's not going to be any extensions for those because a week is a pretty wide window. It's actually more than a week. It's a week after the class ends, the last class of the unit ends. So hopefully this is pretty clear. When you're doing these on your own, these are, if you're not doing them along live with the class in lecture, you can feel free to use any resources you want to answer those questions. No big deal. So basically there's sort of almost like a check to make sure that you're going through the material, that you're absorbing what you're supposed to be absorbing as we go through. All right. So this is just a picture of our current Acorn page as it looks right now. And what you can see on here is where it says Unit 1. Under Unit Quizzes, Unit 1, Introduction and Chemophobia. So this is our first one. It should be live right now. I think hopefully if you can get on right now. And why don't we do our first question? Okay, this is question 1. So if you're online, you can jump in right now. You can answer these questions as we go. First question says, what percentage of your final grade will the unit assignments be worth? A little bit of a trick question because we're dropping 5% off one of those categories, but ignoring that, well, we can go back to our marking scheme here. As you can see, unit assignments are 50%. And so hopefully that one is not overly difficult for you guys to answer. We'll start you off with a few easy ones. Not that any of them are going to be super complicated, but it's a nice example, I think, of a few trial ones to get you started. So in the first unit, I think we have 5. The first unit, I think, will take today's class and Thursday's class. And yeah, we'll go from there. This is the course schedule. So this is just the list of dates that we have for this semester. Starting today is the 19th of January. All of the green squares, the green squares are the days that we have classes. The red ones are ones that we have holidays where nobody has class. And the blue ones is where we have due dates. So in addition to those unit assignments that are going to make up 50% of your grade, there's going to be 2 other individual assignments that you guys will do independently. You will upload to Acorn, and they have due dates of the 18th of February and the 25th of March. So I want you to know about these well in advance. I plan to post the guidelines for the first written assignment basically this week. And that gives you several weeks to work on that. So just so you know well in advance what we're up to here. April 13th, I believe, is the last day of classes for us. We actually have a class that day. And the 2 weeks following that, which are sort of blank on this calendar, are the exam days. And I think, and I might be wrong about this, but I think the last day for the exams period is the 24th. So that's going to get assigned by the registrar. I don't have any control over when that shows up within that period. I think the day that it's supposed to be done is February 12th, meaning that's the day you should know when the final exam for this course is going to be. So my plan for the final exam is to do this virtually because there's a lot of people in the class that virtual is their only option. Cool. I want to put a plug out right now for our Instagram account too. And the Instagram account just started basically today. I mean, it's existed for a long time, since September, but I started posting to it today. So if you want to go to the Instagram account, it's at OChemLukeman. Stands for Organic Chemistry Lukeman, because I used the same account last semester for my organic chemistry class. And these are examples of questions that I gave in my class last semester in organic chemistry, which obviously is a different focus from this course, which is much different, much more general as well. So these questions are really for 2 reasons. They're for fun and they're for practice. They may be, some of these questions for sure, similar to the types of questions you can expect to get on your final exam, and possibly the unit assignments as well. But you don't have to do these. You're not getting graded on this. There's no bonus. There's nothing like that. It's basically just there as a little daily dose of chemistry. If you're looking for that little bit of extra from this course, it's fine. So why not? All right. Academic integrity. I just have some lines here that are basically copied out from the syllabus. There's similar lines are in the academic calendar as well. This is just basically something that you need to be aware of, is that I have expectations in this course, like all of your profs do in all of your courses, that you show academic honesty when you are doing tests, that you do things independently, that when you're doing assignments, you do them first of all independently if it's an independent assignment, not a group assignment, and that if you are using ideas from somebody else or information that somebody else has published, that they are properly cited. Now, I'm not super worried about how you cite them, whether you use APA or whether you use some other method to do the citations. I just want you to know that these are, you have to cite them somehow so that you're giving credit to whoever provided the initial idea and the initial source of the information. And I say that, and it always actually surprises me. Sometimes it's actually kind of funny, the types of academic dishonesty that I see, because the worst one I've ever had is I had a 1-page assignment where they had to do a write-up about some chemical, and they went to the Wikipedia page for the chemical and did a screenshot of the Wikipedia page, pasted it, and submitted it. They didn't even copy and paste the text. It was a screenshot. There was a corner of a picture. There was all the little blue links. Yeah. So yeah, make sure that when you submit work, and not just to me, to anybody, that you're using your own ideas and you are being genuine about where you get the information from. Cool. Now this is a list of the topics that I intend to cover in this course. It's maybe not exhaustive. There may be things in here that we don't cover, and there may be additional things I feel like adding at the last minute. It's one nice thing about this course is the course description is general enough that these topics can kind of come and go. And I like to try to keep things up to date and try to put new things in. And I also like to hear from you what you would like to hear about in this course. And maybe it'll take a few classes for you to kind of get a sense of where we're going in this course. But if you have ideas or you have questions or you think some of these topics are boring but you really want to learn about this, let me know. Send me an email, and I'm very happy to get that kind of feedback because I want really more than anything for this course to be relevant to everybody here that's in the room and everyone here who's joining us online as well, which we're up to 240 people online, so that's pretty good. So yeah, today we're doing the introduction. We're gonna maybe start the chemophobia unit today. Toxins, toxicity, there's a bunch of other ones that you can kind of see going down this list. I don't think you need me to read these out for you. So why don't we start with the very first unit. What I usually do is, the first class is syllabus day if it's a 1 hour class, but for an hour and a half, I like to do at least a little bit, get our feet wet, and take a look at some of these questions. So one of my main, I don't know if you call it a pet peeve, but one of the things I really like to talk about in this course is something which I call chemophobia. And this is a nice example of it. You might recognize what this is in the picture. These are bags of coffee, and these are bags of coffee from Just Us. That's roasted locally. You can get it downtown. Good coffee. And they've changed the packaging in the last couple of years. The old packaging looked like the picture you see on the left, and the new packaging looks like what you see on the right. And the old packaging for their Rise Again claimed on the description of the coffee that their coffee was full-bodied, earthy, and chemical-free. And I'm a chemist, and when I see that phrase chemical-free, which I see all over the place, you see it in coffee, you see it in food, cosmetics, you name it, you can find one that claims to be chemical-free. And when I see that phrase, I start to wonder, what do they mean when they say this is chemical-free, right? What does chemical-free mean? And as a chemist, I would understand everything that we could touch, smell, interact with, see, whatever. I would consider all of those things to be chemicals. So the idea of something being chemical-free to me means like a vacuum maybe, where there's no material at all, there's no atoms, there's no anything. And clearly that is not what they mean when they have it on the bags, right? They actually intend a different message here. But what is that message? What is the message that's on these bags when they say chemical-free? It could mean a lot of things, right? It could maybe mean they grew the coffee beans without pesticides. It could mean they didn't use fertilizer. It could mean when they were roasted, they didn't add anything in the roasting process. There's a whole lot of things that maybe it could mean, or maybe it means all of those things, that it was just grown, roasted, and that was it. But why is it on the bag? It's because many consumers are afraid of chemicals. When they see something contains chemicals, regardless of what the chemicals are or where they came from, a lot of people kind of like, the hair rises on their neck and they start to get anxious about what this product might be because we've sort of been indoctrinated, I think, a little bit by just media, by society, and so on, that if something contains chemicals, it must therefore be bad. And so you see this in things like coffee. And we call this idea chemophobia, which means fear of chemicals, fear of chemistry. And it doesn't mean like you're afraid of the subject chemistry, like you're afraid to take chemistry courses, which sure enough, a lot of people have that one as well. There should be another name for that one. I don't know what we would call that. But no, it means afraid of chemicals, of interacting with chemicals in our ordinary everyday lives. So here's an example. Chemistry set, a sort of a staple. If you're a kid and interested in science, you might have gotten one of these. This is a chemistry set, 60 fun activities with no chemicals. Which makes me wonder, why would you want a chemistry set if you don't want to use any chemicals, right? And of course, as you can see in the picture, there's all kinds of stuff in there that are certainly, in my broad view as a chemist, made out of chemicals as well. All right. So where I see a lot of this sort of chemophobia, this anti-chemical kind of concept, and what we're going to do is, hopefully in this course, dissect a lot of these ideas. We're going to look at how we should be looking at chemicals, how we should be evaluating them, how we should understand their impacts on our lives, as opposed to this sort of gut reaction that a chemical is bad. Okay? So when I go on Facebook, I see lots of examples from time to time, which are actually fantastic source material for this class. One of them was an article. It was actually very well put together. It had very nice graphic artists, baking the graphics. It looked really slick. And the article was called 7 Toxic Reasons to Ditch Dryer Sheets. And I forget who it was. Somebody posted it, and I read it on Facebook. And I was reading it. So dryer sheets, you know what they are. Those bounce sheets that you might throw in with your laundry when you throw them in the dryer to, prevent static electricity and make them smell nice. Their list was a list of chemicals. It was a list of 7 chemicals that they said were either used in the process of making these dryer sheets or were present still. You could detect them in the dryer sheets when you pull them out of the package. And for each of these chemicals, what they did is they went through, they looked up the chemical and looked at the health impacts that that chemical can have on a human being. So the first one, alpha terpineol. It causes central nervous system disorders, loss of muscular coordination, central nervous system depression, headache. Okay, sounds really bad. Benzyl alcohol, also central nervous system disorders, headaches, nausea, vomiting, dizziness, in severe cases, death. It's not really what you want out of your dryer sheets. Camphor, US EPA's hazardous waste list, et cetera, et cetera, et cetera. Now, every single one of these is true. These are all effects that human beings can get from exposure to these chemicals. They didn't lie, they didn't make it up. Does this mean we should ditch dryer sheets? That the advice that they come to as a result is true? Well, having an education in organic chemistry, I was looking at this list and I recognized a lot of what these chemicals are, right? Alpha terpineol is the main aroma compound produced by lilacs. So if you have a lilac plant that's blooming, usually May or June, very intense smell, that smell is alpha terpineol. That's the chemical the plant is putting out. Benzyl alcohol is the main flavor and odor compound that comes from jasmine flowers. So if you drink jasmine tea, there's benzyl alcohol in jasmine tea. And the flowers, if you smell the flowers, you're going to be inhaling this compound as well. Camphor is in rosemary. In fact, something like almost 10% of the dry weight of rosemary, like the seasoning you would put on like turkey or whatever, is that chemical, camphor. And you can keep going. Ethyl acetate is present in wine. In fact, when they talk about wine, they often say it's either like fruity or dry. And the fruitiness of wine is a measure of how much ethyl acetate is in the wine. So a lot of ethyl acetate is a fruity wine. Smaller amounts are less fruity. And linalool is found in all kinds of things like roses and so on. Lots of different types of flowers produce linalool as well. So if you look at these things, there are aroma compounds that you find in flowers. There are aroma compounds that you might find in spices. Why do you think they add these things to dryer sheets? Because they smell nice, right? They want your clothes to smell nice. You want to smell your clothes coming out of the dryer. If you put your face into a bunch of lilac flowers and took a big sniff, are you going to have central nervous system disorders, loss of muscular coordination, central nervous system depression, and headache? No. Probably not. Benzyl alcohol can cause death. If you drink a cup of jasmine tea, is that going to kill you? No. But if you took a liter of pure benzyl alcohol, that would be, hundreds and hundreds of tons of jasmine flowers to produce that much. But if you took a liter of pure benzyl alcohol and you drank it, you're probably going to die. So while all these things about these different chemicals are true, if you're exposed to huge amounts of these over a short period of time, it doesn't mean that these chemicals are inherently dangerous to us and that we should inherently be avoiding products that might contain them. Because when you are exposed to a chemical, the effect that that chemical can have on you is very strongly dependent not only on what the chemical is, but how you're being exposed to it, how much, over what period of time, are you inhaling it, are you injecting it, and so on. So oftentimes when I see people posting articles and so on that are warning you about chemicals, that's the mistake that's being made, is they're not thinking at all about the route of exposure. And what almost always follows these types of articles is a link to a store that'll sell you a chemical-free version of the same product. Okay? So there you go. That's the first maybe takeaway is be wary when people are trying to sell you something and they're talking about chemicals. There we go. Here's another example. Potassium chloride, you can see in Dasani drinking water, is one of the ingredients, KCl. Potassium chloride is actually a source of potassium for us nutritionally. It's a good thing, I guess, to have in certain amounts, not too much. But potassium chloride is also used to stop the heart in lethal injections. So if you take a highly concentrated solution of potassium chloride and inject it into your bloodstream, that will cause your heart to stop. But does that mean that drinking very small amounts of it in your water are a concern? Or in fact, they might be a very good thing. It's still up there, right? You'll tell me if it's not, right? All right. Okay, so what I hope to teach you in this course is, in one level, maybe 10, 20% of this course is sort of some basic concepts in chemistry that we need to know to apply to some of these issues that we're going to be discussing in the course. And if you've already taken a lot of chemistry before, if you've taken it maybe even like high school, especially first year organic or past that, that 10 to 20% of the course will be review. It'll be, yeah, okay, I know that already. But if you have done zero chemistry ever, we're going to start at the basics for where we come from, for there. So please don't feel intimidated if you've never taken any chemistry before in your life and you're in this course now wondering if you should be here. Yes, you should be. We will make sure that all of the knowledge you're going to be needing to understand the issues that we're going to be discussing, which is the other 80%, is going to be put there for you. So the first thing that I need you to know is that matter is made from atoms. Atoms are the smallest, we say indivisible unit of matter, but they're not technically indivisible. You can split atoms. But let's say pre-1900, people weren't splitting atoms, or we didn't know about atoms that could split. Very, very small. The actual name atom comes, A means not or without, and tom means to cut. So the word tom, you still see it in certain words like tonsillectomy. So the tommy at the end, tom, means to cut. So a tonsillectomy is you're cutting out your tonsils, right? So tom means to cut, and A means not. So atom means cannot be cut, right? So the actual word suggests that atoms are not divisible. Everything that we see, we smell, we sense, the air, everything are made up of these same particles we call atoms. So we have table salt here. What we see are little crystals of salt. If you pour it out on your food under a magnifying glass, they look like the picture you see here on the right. But if you could zoom in at the molecular level, you would see atoms, two different types, sodium and chlorine. and they have charges in this particular case, and they're arranged in this what we call cubic pattern in NaCl, and that cube can grow very, very large. And if you look under a microscope at salt crystals, they're little cubes as well. And it's on the atomic scale, scaled up to the particle we can see with our own eyes. They still maintain that same cubic structure. So yeah, matter is made from atoms. Atoms are basically made of subatomic particles. So there's some smaller particles that atoms are made from. Protons and neutrons come together and form the center, a dense nucleus, and then surrounding the nucleus are another type of particles called electrons. So protons, neutrons, and electrons make atoms. And it turns out that if you have two atoms and they have the exact same number of protons, neutrons, and electrons, those two atoms will be identical in every way. So what does that mean? That means if you have a carbon atom that's in a tree that you find in the middle of an old growth forest, or a carbon atom that's in a molecule of crude oil that you pulled up out of the ground, or a carbon atom that landed on Earth from a comet, those carbon atoms are identical in all of those three cases. We would not be able to distinguish those atoms if they have the same number of protons, neutrons, and electrons. Make sense? Oh, look, we got another question. So if you have your acorn open, what subatomic particle is not found in the nucleus of an atom? Nucleus is the center. This one's not so tough either. Does anyone have an answer for me for this one? Nobody. It is big class, yeah. Yeah, the electrons are the ones that are not in the nucleus. The protons and the neutrons are in the nucleus. And yeah, thank you very much. It's tough for the big class like this to get a lot of feedback. I typically don't get too much. It's more like a monologue, but hopefully don't feel intimidated. If you want to speak up or ask a question or answer a question, God forbid, please do. Okay, so atoms are identical. Regardless of their source, regardless of where they came from or when they were created, they're identical if they have the same number of protons, neutrons, and electrons. Molecules are slightly larger chunks of matter that are made by bonding a set of atoms together. So if the atoms are all identical, if all the carbons are identical to all the other carbons, if you build two molecules out of the same atoms, the molecules will also be identical. Assuming those atoms are arranged in the same structure, it's like if the atoms are identical, the molecules are also identical to each other. So what this means, if you have a molecule, let's say in this case, this molecule, this is a structural drawing that we don't deal with in chemistry until organic chem. So please don't feel you have to look at this structure and interpret what this means or what all those bonds and lines and stuff are. That's just there. If you know it, great. If you don't, no problem. This is a molecule called vanillin. And vanillin is a molecule that is produced by the vanilla plant. And it's the chemical that is responsible for the vanilla flavor, the vanilla smell, and it's what we consider to be the essence of vanilla. You can either have vanilla produced in the plant by the vanilla bean, and you can extract it out, and we call that vanilla extract. Or you can make it yourself. Well, human beings, we can make vanillin synthetically, starting with all sorts of different starting materials by a different process by which then the plant makes it. Yet what we still have is the same exact molecule, because we can make the same structure with the same atoms in the exact same arrangement, meaning these two molecules are identical. The molecule of the natural is identical to the molecule of the artificial. Okay, so I actually have some props here. Where's my other prop? Found it. Okay. So I usually pass these around, but I don't think I can pass them around this year. This is the natural vanilla. I'm going to hold it close to the camera. I'll pull this out. I thought that was plastic. Sounded like glass. Basically, they're these long kind of, they look almost like a elongated raisin. Very nice smell to them. These are vanilla beans. And if I took these and soaked them in an alcohol and water solution, in fact, one of the best things you could use if you want to make your own vanilla extract is just vodka, sort of a pure solution of ethanol and water. You could soak them in there, and over days, weeks, you would have vanilla extract. The actual chemical that is responsible for the smell and flavor is vanillin, and I have a little bottle of it right here. And this bottle, I'm just going to switch my view for the online people. This bottle is, it basically just looks like a regular white powder, nothing particularly interesting about it. If you take the top off and you smell it, it smells like the vanilla beans, it smells like vanilla extract. It's this chemical that's in the plant, it's this chemical that's put into your flavoring, into your perfumes, or whatever else vanilla is added to. There we go. It all went all over my iPad here, so we're good now. So when you go to the store and you buy vanilla extract, there's two main types that you can get. You can get natural vanilla extract, which is really expensive, especially now, or you can get artificial vanilla extract. What is the difference between these two? Well, the natural comes from a plant. The plant is actually very, very fussy about where it'll grow. It will not grow here in Canada. It grows, I think something like 80% of the world's supply is grown on the island of Madagascar, that it has this sort of specific type of climate that's best for growing it. But you can grow it. It looks like this plant you see on the left. You can see those green pods form. And those green pods, the plant produces a chemical inside the thing, which has the structure you see on the bottom left, which again, don't worry about the particular structure. Then what happens is you can pick the things, or you can leave them on the actual plant, and over a period of about 50 days, they dry out, they turn brown, and they, what we say they ripen. And after those 50 days, you can pick them and you can make your vanilla extract out of them. What happens during that ripening process is that molecule you see on the left basically just splits in two. It produces the vanillin, which you can see in this bottle, and it produces a molecule of glucose as well. So it produces a little bit of sugar in there as well. So after the 50 days, you can make your vanilla extract. Vanilla wasn't really known, though, to Europe until about 140, 150 years ago. It was sort of an unknown flavor. And when eventually vanilla started to get shipped to Europe, it became extremely popular. And it's still extremely popular today. It's one of the top flavors, right? Top 3 ice cream, maybe? I like vanilla a lot, actually, vanilla ice cream. A lot of people say that's boring, but whatever. Vanilla ice cream's good. Very quickly, the demand for vanilla outstripped the supply. Vanilla is hard. You can't just grow a field in the middle of Alberta full of vanilla. It's not like corn, or it's not like wheat, you know? It's very difficult, it's fussy, needs the right climate, and they weren't able to keep up with demand. So what the chemists of the time did is decided, maybe there's another way I can make vanilla without having to grow this really fussy vanilla plant. So what they did is they picked a different, more abundant flavor spice called eugenol. Eugenol is about 50% of the weight of cloves. So whole cloves, which is what's in this picture, has this chemical eugenol. They discovered that they could do a couple of chemical steps on eugenol and convert it to vanillin. They could take cloves and they could turn cloves into the same chemical that the vanilla plant was producing. And this is one of the things that chemists try to do, is find ways to make abundant supplies of chemicals that are maybe found in nature only in very, very small amounts. So for example, there's some exotic sea sponge that produces 1 milligram a year of some chemical that's really good to fight cancer. Well, we want that chemical, but we can't harvest enough sea sponge to make that viable. Can we make that same chemical through some other pathway. And if we understand that two chemicals, two molecules, are identical in all properties if they have the same atoms, then this scheme will work. And in fact, it does. So making vanillin from cloves, like you see on this slide here, dropped the price of vanilla by about a factor of 4. Although cloves are still fussy, they're still hard to farm. Like you can't, they're still expensive. I don't know how many of you are buying cloves frequently, but they're one of the more expensive spices to buy. So it's helped. It increased the supply, but it didn't solve the problem. There's been a number of other improvements. In fact, in the 1980s, Canada produced like 90% of the world's supply of artificial vanilla out of a single plant in Quebec, and it used waste material from pulp and paper mills to make it. And they've changed the pulp and paper process since to be more environmentally friendly, and as a result, they don't use that process anymore, so Canada doesn't produce really much of this at all. But most of the vanilla produced today, and I'm not sure about the vanilla in this bottle, how it was produced, starts as crude oil, which kind of sounds gross if you think about it. We're eating stuff in our food that started out as crude oil. But think about it. The chemical that was produced is indistinguishable from the chemical produced by the actual plant. It's identical in every way. Does it matter if it started out as oil? Does it matter if it started as carbon dioxide that the plant brought in? No. The chemical is identical no matter what. The actual process here is there's a carcinogenic, that means it causes cancer, a cancer-causing chemical found in crude oil called benzene that you can do a few reactions to and get the molecule on the left. It's called guaiacol. That particular chemical is an important flavor compound in the fresh aroma of freshly roasted coffee. So you find this same chemical in all kinds of different things. A few more steps, you have this white compound. And the reason I say I don't know where this came from is we have in our labs a bottle that was purchased probably 50 years ago. And I don't know if the oil process was used to make it then. I don't know if it was the pulp and paper process. I don't know if this came from a plant. I have no idea. And the interesting thing is there's no test I can do to determine where this came from. This is indistinguishable from the same chemical produced from any other source. So maybe this is another chemistry lesson for you, is that how dangerous or toxic or whatever you want to think about a chemical has nothing to do with the chemical's history, has only to do with the chemical's structure. So here's an example. We have on this slide a picture of sodium metal. Sodium metal looks like a nice shiny metal like most metals you're used to, except it's very soft. You can cut it with a knife quite easily. Not as soft quite as, maybe like if you had butter that was frozen, it's about that soft. So you could cut it with a sharp knife. You throw it in water, and you get the reaction that you can see here on the screen. It kind of sputters and catches on fire, and if you had a large amount of it, it's quite spectacular. Chlorine gas, it's an element. Chlorine, the gas itself is a green gas. We're going to talk about it later in the course. It's very, very toxic. It's used as a poison gas in World War I. You can react these two together, and you get that sodium chloride that we talked about before. And sodium chloride, we had decided, or hopefully you agree with me, that sodium chloride itself is not very dangerous to us. It's not very reactive. It's fine to eat. In fact, it's not only fine to eat, it's a required nutrient for us. We need salt to survive. Too much is bad, of course, and most of our diets probably have too much, but generally speaking, it's a very good thing for us. So the point here is that even though this chemical could be born from two extremely dangerous and reactive chemicals, it doesn't tell you anything about the new form, sodium chloride, how reactive or dangerous or whatever it might be. It doesn't have the same properties as the two chemicals it was made from, sodium and chlorine. Put them together, you get a completely different set of properties, completely different substance than you had before. All right. There's actually a new way now of making vanilla, and it's starting from rice bran. So the rice bran is sort of like the outer husk, I guess, of a rice kernel. And when you buy rice, this is usually removed first. And you can take that rice bran, which is generally considered a waste product, and you can take that and you can put it through a biochemical process. You can treat it with a bacteria and a fungus in sequence. And after about 50 days of culturing with this rice bran, you get this big slurry of stuff. One of the components of that slurry is vanilla. You can do then a refining step, and you can get this same pure white substance out from that process from the rice bran that you could get the same thing from the oil or from these other processes as well. You get about 6.4 grams of this stuff for every liter of that slurry that you start with. And it's about 10 times more expensive, this process, than getting it from crude oil. Yet there is a market for this. People want to buy the vanilla powder that comes from this expensive process. It costs a lot more. It's much more expensive than buying it from another source. But there's a reason why people want this. And the reason is actually kind of funny. It's a regulatory thing that because this was made inside of other organisms, whether it's a fungus or a bacteria or whatever, this can legally be called a natural flavor. Even though it's made through what I would consider to be a very unnatural process, right? It's very artificial. The refining step is also very artificial as well. You get this, but because this was not made by human beings directly, all of the chemical changes took place inside of an organism. This can legally be called a natural flavor, and people are terrified of food when they flip it over and read the packaging and it says artificial flavor. Even though I would argue the molecule produced here is indistinguishable from the same molecule produced from the artificial process. So the takeaway message from this maybe is if you have a compound that comes from a natural source, if we can make a synthetic copy of it, it's identical. It's no different, and they're not more toxic, they're not more dangerous, etc. The biological activity of a molecule, of a chemical, depends on its chemical structure and other things like its dose and the amount and all these sorts of things. But the chemical structure is what makes a chemical, not its origin, not where it was made, when it was made, how old it was, these sorts of things. Okay. Let's do question 3. Vanillin is the molecule responsible for the vanilla flavor and smell. Chemically speaking, how is the vanilla molecule produced by the vanilla plant different from a synthetic copy produced in a lab or factory? A, and by the way, this A, B, C, D might be in a different order for you. I think that's randomized, so everyone gets sort of a different order and things like that, but the responses should be pretty much the same for everybody. The version produced by people, the artificial version, is safer because it's artificial. B, they have the same structure, so they have identical properties. C, the version produced by the plant is safer because it's natural. Or D, they have different structures, so they have different properties. Hopefully you agree with me that the correct answer here is B, they have the same structure, so they will have identical properties. All right. How are people feeling? Is that good for class 1? I know we still have like half an hour, but like I already kind of cheated you a little bit because usually the first class is sort of syllabus day anyway. I did go a little bit into the material. We got 3 of our questions done. I think I'll call her quits right now. We'll pick things up where we left off today in Thursday's class. And today I think who I invited was everybody who said they wanted to come in person as much as possible, and even I think student IDs, what I might just say is if you indicated you wanted to come in person or 50-50, you can come next class. Because obviously we have a lot of seats, a lot of space, and hopefully we sort out the AV issues with these other TVs here. If not, what you might want to do is just bring some device where you could have the stream open at the same time. And if you have the stream open, then you should be able to see the slides at least, what's on the board here. So thanks for everyone for coming. Thanks as well to everyone who's here online. And these lectures will be available for you. They will be posted on YouTube, that YouTube channel. And I'm not sure if the link I already posted will still work, but if not, there you go.